So, good morning, students. Today we'll continue again with reading number 4 and topic number 6, which is Lacey's theory, the design procedure, and fixing the longitudinal section of the canal and other design considerations, and layout and components of storage and diversion headworks in a canal. First, design procedure for Lacey's theory. The first step is that we have to compute the silt factor f, that is f is equal to 1.75 root over d suffix minimum, where d suffix minimum is the average particle size in mm. And next, step number 2 is calculating the velocity of flow from the following equation, which is v is equal to qf square divided by 140 whole to the power 1 by 6 meter per second, where q is discharge in q max. So here it's the table shown for values of average particle size, d suffix mm for various types of alluvial materials. The type of material, that is the soil, and the average grain size in mm is given and shown in this table. You can go through it. Third step, computing the cross-sectional area of channel section by capital A is equal to Q by V. Fourth, computing the wetted perimeter of a channel section, that is P is equal to 4.75 root over Q, where P is in meter and Q is in meter cube per second. Step number 5, working out the hydraulic radius by mean depth, that is capital R, from the following equation, which is R is equal to 5 by 2 into V to the power 2 by F, and comparing the values to obtain with the value of hydraulic mean depth computed by using the following formula, which is R is equal to A by P in meters. Next, knowing the values of A and P above, the channel sections, that is the depth Y and bottom width B, is then determined. Finally, we determine the bed slopes capital S by the following equation, that is S is equal to F to the power 5 by 3 whole divided by 3340 into Q to the power 1 by 6. Next is fixing the longitudinal section of the canal and other design considerations. Related to Kennedy and Kennedy's theory and Lacey's theory, I'll give you some numericals based on the design procedure, and now we'll continue with fixing the longitudinal section of the canal and other design considerations. So if a channel is designed according to Lacey's theory, it shall have a fixed slope and fixed section for a given discharge and silt factor. But on the other hand, if the channel is designed on Kennedy's theory, it can have different sections for different slopes. So in practice, it has been found out that Lacey's slope equation gives excessive slopes. The slope of the channel is, however, fixed on the available country slope consistent with economy. A steeper slope governed by maximum permissible velocity will be economical but will lower the FSL, causing less irrigation area. Hence, the maximum possible irrigation coverage would indicate flatter slopes governed by minimum permissible velocity. A via media between these two limits must be adopted for selecting a suitable bed slope of the channel. If the chosen design slope is found to be flatter than the natural available slope, the difference can be adjusted by providing suitably designed drops. But if the design slope is steeper than the available, then adjustments are made to change the design slope so as to make it near the available slope as possible. Since a change in depth causes non-uniform flow, it is desirable to change the depth as less as possible. For this reason, the channels in the upper reaches are generally designed with large bed width to depth ratio. Suitable adjustments in bed slope, depth, etc. can be made for fixing FSL on various considerations. After fixing L section of the channel, and the cross section can or may be fixed on the basis of various canal standards. Next, other design considerations. Design procedure. Number 1, the longitudinal section of the existing ground along the proposed canal alignment is plotted on a suitable scale. Number 2, a suitable channel slope is assumed. Number 3, a slope line is marked for drawing FSL line, keeping in view the guidelines already given. Number 4, the channel is designed from its tail ridge to its head ridge, kilometer to kilometer. Number 5, the discharge required in the channel in the given reach for required irrigation potential is worked out and losses are added so as to calculate the required discharge. Number 6, the bed slope, FSL, falls or drops, etc. adjusted using intelligence, judgment, and knowledge. The bed levels, water depths, etc. are drawn on L section. The X section at every kilometer is drawn on L section. Layout and components of storage and diversion headworks. Irrigation canal takes its supplies from a river or a stream. In order to divert water from the river into canal, it is necessary to construct certain works or structures across the river and at the head of the off-taking canal. These works are known as diversion headworks or headworks. The canal headworks may be classified into the following two types. Number 1 is storage headworks and number 2 is diversion headworks. Storage headworks consist of a dam constructed across the river to create a reservoir in which water is stored during the period of excess flow in the river. From the reservoir, water is supplied to the canal in required quantity as per demand. The storage headwork stores water in addition to the diversion into the canal. Diversion headworks serve to raise the water level in the area and divert the required quantity into the canal. The various purposes served by diversion headworks are as follows. Number 1, they raise the water level in the river so that the commanded area is increased. Number 2, they regulate the supply of water into the canal. Number 3, they control the entry of silt into the canal. Number 4, they will provide some storage of water for a short period. Number 5, they reduce the fluctuations in the level supply in the river. Next, component parts of weir or barrage. A diversion headwork or weir usually consists of the following components: weir or barrage or proper, undersluice, divide wall, fish ladder, control head regulator, silt excluder, silt ejector, river training works, guide banks, marginal bunds. A typical layout of weir or barrage is shown in the figure. And regarding the component parts of weir or barrage and regarding the typical layout of diversion headwork, we'll see a video now. It is long, but it will help you to understand more about diversion headwork in detail. So this is your assignment for lecture number 29. The question is you have to write in detail about the automatic water level control gates for irrigation canals. I repeat, you have to write about the automatic water level control gates for irrigation canals. I have already shown you a video related to this topic. The last date of submission is also given here. Now you can give your attendance in the chat box, and at the same time now we'll go through a video showing diversion headworks, which is very much important. So that's all for this lecture. Thank you.
Hello everyone. Today we'll discuss about a topic called diversion headwork. So a diversion headwork diverts the water in a river to increase its height and to supply it to other areas for different purposes. In this case, let us look at a diversion headwork called the Bordekodai Headworks, which is located near the place called Sijusa, near the Arunachal border. Let's look at the components. This is a barrier across the river. As you can see, this is the river and this is a small barrier. It raises the water level, and as the water level rises, it can be diverted across the banks to a canal. So this is canal. So through this canal, water is supplied to the nearby agricultural fields. So you see, this canal is coming like this, and from this, different branches are shooting off to the irrigation fields, the agricultural fields. Now, if we look at the whole project, this is the main weir, or it's basically a barrier which raises the water level, and this is called a divide wall. This is another divide wall. The divide wall serves one purpose, that is, it prevents the formation of secondary current. Secondary current is when water flows in the other directions than the straight direction of the axis of the river. So some eddy currents are produced. To stop these eddy currents, we divide this portion of the weir into one or two parts. So what happens is those secondary currents cannot form because of this barrier, this wall, and near the place from where we are going to extract the water from the river, those kind of eddies are not formed. So here we have a relatively calm pocket of water. Now, let's look at the other components. You see here, this cross-section is very well defined, unlike the river cross-section in all these other places. So that is done by constructing a kind of an embankment here. So this is the embankment where the upstream end of the embankment is made a curve like this. What should be the actual specification of this embankment will depend on the discharge, the river width, and lots of other factors. So in this side also, we can provide the same kind of embankment, which will prevent the erosion of the river. That means from this point up to some point in the downstream, we need the cross-section of the river to be stable. Now, this place, as you can see, here we have all the gates. Those gates, when opened, will let water from the river to enter this canal, and when closed, the canal will remain dry. Now let's look at a clearer picture here. So this here is the river, and this is the guide bank or the embankment that is provided to protect the bank. And this is the weir, this is the divide wall, this is the canal headwork, and this is the canal from to which water is supplied. There is another embankment which is called a marginal embankment. It can be provided on one side or both sides depending on the topography of the area. In this place, it's not clear whether that embankment is provided or not. That embankment is provided for a very long distance actually, because this embankment, which is provided here to protect the bank from erosion, is expensive, and it's constructed with rocks and boulders. But a longer embankment can be provided up to a larger length along the river up to the upstream, so that because of this embankment and this weir, the water level is raised permanently, and therefore if flood comes, the flood level will also rise. Therefore, to protect the nearby area, we provide an embankment along the river bank to a certain length. How much length is required? That will depend on the topography. If the river banks are already very high, then that embankment may not be necessary. So this is that embankment here. Now, if we zoom in, then we'll see this kind of a structure. That is, this is the weir or barrage. This is the off-taking canal. This is called undersluices. These undersluices are some extra gates right in front of these other gates. These gates will allow water to enter the off-taking canal. But here also there are some gates. Those gates, when open, will allow the river water to flow downstream. So these gates are opened by some amount so that some water always reaches the downstream, because the downstream cannot be allowed to go dry. Now, this portion, which is just in front of this off-taking canal, is called the approach channel or pocket. Here, the water is generally steady and calm because no secondary current is allowed to form, because we have provided this divide wall here. And in this divide wall itself, we can provide something called a fish ladder. We'll see how this fish ladder works later. And this is a structure which is called silt excluder. This is provided so that the silt is trapped inside this and it cannot enter the off-taking canal, because this is a canal which is used for irrigation purpose, and if silt enters this canal, then after some time silt will be deposited in the canal and its bed will be raised and its capacity will be decreased. Now, let us look at this structure from a 3D perspective. So this is the structure from the top view. These are the embankments, the guide banks or guide bunds. This one and this one, they are the marginal embankments, which will be provided for a very long length to the upstream, so that it is the upstream, that means this area and this area are protected from the raised water level. Now, this is the off-taking canal. This is the weir, and this part is just a road or a bridge over the whole structure so that some transportation is possible. Now, the scale of this whole project may not be very accurate. Just to give you an idea, this is a figure of a person, so you can guess how big something can be. Now, this is the embankment that is provided, and it is provided with a curved head, and the downstream end is also provided with some curve. So water comes in from this direction, and here it is stored and the level is raised because of this weir, and this divide wall makes sure that in this portion the water is not having lots of secondary currents or eddies. Now, this portion is called a fish ladder. It's a long channel connecting the upstream and downstream of the weir, and it is provided with these kind of small walls projecting from both sides of the canal. What happens is, water, when flowing through this, will have to take a very zigzag path like this. And therefore its velocity will be reduced. When its velocity is reduced, fish from the downstream can possibly swim upstream, because now those fish have to overcome only a small velocity of water. Otherwise, it is very difficult for them to swim upstream and cross this barrier. Now, the off-taking canal is fed by these kind of work, which is called a head regulator. So a head regulator is provided with these kind of gates. So these are the gates. Mostly these are made of metal and they are raised or lowered based on need. So here I have only shown this kind of a steering or screw thread arrangement. If you rotate this, it will be either lowered or raised. But in most cases, instead of this kind of an arrangement, some machine arrangement is provided where a motor, electric motor, generally rotates a spindle, and that spindle raises or lowers a gate. Now, this is something called, this part, these tunnels are called silt excluders. What they do is, when water flows to this location, the silt carried by the water will be mostly carried near the lower part of the flow. So that part enters this portion, these tunnels. If you see, those tunnels lead to the downstream. These are some more gates here, here, here. Each of those gates are supposed open by a different amount. Now, in this part, all the silts that are carried by the water will be stored and trapped, so that water entering through these openings will be relatively clear, and therefore in this canal we get some cleaner water. So this canal will go a long way based on the command area. Now, there is something else called an undersluice gate. So these undersluices are, again, gates. So these gates are opened or closed. So these are the gates. These are opened or closed based on need, so that water from the upstream can be released to the downstream. Generally, they are not closed together to the complete extent. Only a few of the gates are closed, or they are partially opened, so that a controlled amount of water is released to the downstream. So this is what a diversion headwork looks like. I'll share this file with you, and this is prepared using a software called Sketchup. This is Sketchup Make 2017. It's a free software where you can draw some kind of 3D diagrams. It may be useful for you also. It's very simple and easy to use actually. There is a pro version, which is, I guess, you have to pay for that, where instead of surface diagrams, here you see all these solid, although they appear to be solid, they are not actually solids, they are just made of surfaces. So their insides are hollow. Now in SketchUp Pro, you can use, draw proper solid diagrams, but for most of the purposes that we need this SketchUp Make, the free version is sufficient, I guess. One more thing, you see, I've made from here to here, there is a floor. So this is called the weir floor. Now, that means this portion and this portion is not just a river bed. There is a concrete or impervious floor, concrete or masonry floor, which is provided from here up to here. This is provided so that water doesn't enter the river bed very close to the weir and doesn't get released just at the downstream, because in that case, it will be a very small seepage length and lots of seepage will occur. So it will not be able to store the water. So what we have done is we have provided some impervious floor so that water cannot enter in this portion. Water has to enter here in this location, and it has to flow under the ground, under the floor, and through this it can release at this portion to the downstream. That means we have increased the flow path. To further increase the length of the flow path, what we can do is we can provide some sheet piles here. Let's provide this sheet pile here. The sheet pile will not have this kind of thickness, but here in the drawing, I'll just to show you, I'm giving it some thickness. So this will be an underground wall or sheet, so that when water enters here, it cannot directly flow horizontally. It has to go down a little bit, then again come up, then only it can flow horizontally. A similar sheet pile can be provided at the downstream end also. Actually, it must be provided in the downstream, that we are going to learn after some classes. So here also we are providing another sheet pile. So these are called cutoff walls. So now you can see water has to enter like this, then it will go like this, then it will flow horizontally, then again it will come back like this, and it will be released at the end of this impervious floor here. So we have vastly increased the length of travel of this seepage water. That means its velocity will be reduced, and therefore the rate of seepage will also be reduced. So this is how we can understand the different components of this divergent headwork. So that's all for this one. If you have free time, you can install this Sketchup software and try your own drawings. Okay, thank you.